Hi everyone, I'm Jesse. I'm a fifth year Mechatronics and computer science student, and hopefully I'll be giving a presentation on an introduction to image processing, what image processing is, what is useful, as well as kind of an overview of OpenCV and how to use it. So first thing, what is image processing? So you might think of how our brains interpret images, our eyes, we take in information. But images really to help us understand the world around us, right? So, humans use our eyes and then our brain to process images. And from that, we can segment out information to help us understand the world around us. Our brains are like the best thing for image processing. They've evolved to be able to determine lots of different things, but a robot is really hard to do this. So this is why this whole area of study, image processing, to try and help robots understand the world around them. So instead of eyes, they have cameras. Instead of a brain, they have a computer. So what kind of things are we looking for when we're interested in images and trying to get robots to understand the world around us? The main, if you kind of want to think about the most basic principles, the main sort of thing we're interested in looking for is depth, color, and motion. At least for a human, this is kind of the main thing that the brain responds to. As mammals, humans in particular, we have like forward-facing eyes, which is really good for depth perception, as well as color understanding. In fact, most predators, like if you look at like cheetahs and birds of prey and stuff, they all have forward-facing eyes, so eyes at the front of the head. And the reason this is because it really helps with color and depth understanding, to really understand the world around them. So, when they're hunting, how to accurately grasp the food in front of them if they're chasing down a prey or something like that, or accurately determine where something is at great distance away if you're moving at a super fast speed. Other animals have a different type of understanding of the world around them. So a lot of non-predators like herbivores and things like that have, if you look at like deer and stuff like that, they have eyes at the side of their head. And the reason this is because it kind of gives them this 360-degree view of the world, but it reduces clarity of color, but it really helps with movement. So they can pick up movement a lot more easily. And so this is actually why predators move super slowly when they're approaching their prey, because movement will be picked up, but color, not so much. With humans, what we're trying to look for when we see an image is we try and understand the depth of an object, as well as kind of its motion, right? So if you kind of look at these images, which are just sort of, I took them from the Matrix. When you're looking at something, we can estimate how far away something is just by the visual information. There's no extra information. All we have is just the color. And if we look at this GIF here, we can infer motion. Things moving. So all it is just a bunch of still frames, but the thing is moving, and we can infer direction from that motion and speed. But really, to a robot, this doesn't actually mean that much. Motion is a really tricky thing to understand. So these three pictures here are basically the last 3 frames from the previous GIF I showed you, right? But how do we know that? We know that this bullet is in motion. We only know that from the context of the previous slide. Is the bullet getting closer or is it getting bigger? From a single frame, we can't actually tell this information. And this is why image processing is really important, but also why image processing is really hard. Because as humans, we understand context and robots don't. So these are the kind of things we have to start to consider when we think about understanding images. The other thing that images provide, so we've talked about depth and color, as well as motion, is images actually provide a lot of information about the properties of material. So just visually, human brains have evolved to determine, what something might feel like just because of the way it looks. And a lot of this has to do with light, the way light refracts through things, the way light reflects off things. And this can tell humans really important things about the property of the object that they're looking at, right? So if we look at this image in the bottom left here, it's basically like a grayscale image. So there's no color involved, right? So that's not giving us information. But if we look at this, we all know the we can all kind of imagine what the property of this material is, just based off the visual qualities of the light, and we can infer the texture of this material. You know, it's kind of rough, it's reflective because we get these little like cracks around the place. You can see it reflects and refracts differently here to here. So this is probably smoother than this section over here. And this ball we know is super reflective, not because it has any color, but because of the way the light reflects differently off it, right? So just an image can tell us a huge amount about the world around us. In addition, there's no color in this image, but we can, as humans, we can tell this ball is separate to the ground here. And that's because it has different texture qualities, right? This is reflective, while this is cause. And the only thing that's telling us the difference between these two things is the way, well, is basically the way the reflectance qualities of the ball differs from that of the ground. And as humans, we can understand that because we understand the difference between reflection and not, or the different kind of surface, the way something might react. Robots don't. So this is something else we need to consider, you know. We know what this tennis ball might feel like. We can expect this tennis ball to have certain properties because we've seen it before, we've experienced it before. How do we know that this tennis ball is soft, right? What features of this image tell us that the ball has certain qualities? Now, this is kind of a trivial example, but we'll see in a sec that these things actually help humans in a way that might help robots. So how can we take that understanding into it from our understanding of images and get robots to try and understand the same things? So this is kind of an example I thought would be useful about actually how texturing and light is important to understand the world around us, because this kind of prelude is just about how images help us understand the world and why it's important for then robots to try and get robots to do the same thing. So this is basically a before and after photo of a unrealistic versus a realistic rendering of a scene. This is done using Blender, which is a rendering engine. And basically the only real difference between these two images are this image has reflectance qualities, or this texture has reflectance qualities, and this image does not. That is actually the only difference in the rendering. In this one, the image is getting, the ground is given texture. Oh, sorry, the ground is given reflectance, and in this it is not. But that actually tells us a huge amount about the information. It tells us a huge amount about the scene. So in this one, we can infer a whole bunch of information about the ground, what its properties are. Is it safe to walk on? What might it feel like? All just from the reflectance of the ground, which can be important for a robot if it wants to navigate around a natural environment or climb upstairs or something like that. Right? So these are the kind of things we need to consider when we talk about image processing. So what is computer vision? Computer vision is trying to get a robot, a computer, to understand this information. Computer vision and image processing are sort of used interchangeably. They are slightly different. This is an active area of research. This is continually still growing field in robotics, in computer science, in all these areas. So one of the problems with image processing, we've talked about context, motion is hard to understand. Taking one frame out of context, if you just analyze it by itself, is not going to be as useful as if you have lots of images in a row and you understand the motion between the images or how color changes, or you understand the environment. This kind of can be associated with the fact that images are very high dimensional data. So they have lots and lots and lots of information inside them. So if you take a 1024 by 768 image, This has more than like 3 million bits of information in it, just raw data, right? So to try to analyze each of those by themselves in the kind of way that we're used to analyzing data is really, really tricky because there's so much information. This is hard from a programmer's perspective because you have to think about how each thing affects each other, and we can't possibly understand that. And the other thing is that it's computationally expensive. And so it can be quite slow to interpret all this data. So how do we actually go about interpreting and analyzing images? What are the basic techniques that we're going to be looking at? Before that, I'm just going to go very briefly over what actually is a digital image. This is the kind of core of how we do analysis, and for people who haven't done any image processing before, this is the kind of basis of that. So a digital image, basically a matrix. Its width, its height, and how many channels it has. A basic image that we're probably all familiar with, JPEG, PNG, file you see in your computer, a 3-channeled matrix. So there are 3 channels, there are 3 matrices lined up next to each other, and they represent the red channel, the green channel, and then the blue channel, which are the 3. And between these, that basically makes up all the colors in the spectrum that we see. So each pixel, which is the basic unit of an image, is made up of a 1×3 vector. So a pixel at position 0, 0 is going to be made up of the R value, the G value, and the B value. Right? For an image of a different size, the pixel is going to be a different dimension. So if it's grayscale, it's going to be 1×1 vector. And for an image that's encoded with 8 bits, so JPEGs are often 8-bit encodings, but you can go up to more if you want more information stored. They range from 0 to 255, where a pixel that is 255, 255, 255 at any location is white, and 000 is black. So if we take a look at what an image might look like at the pixel level, we take a grayscale image, which is just one matrix, ranging from 0 to 255, where 55 is still white and 0 is black and everything between is gray. We look and see that this is what this section of this picture might look like, and then how this gets translated to a matrix. All right, so all of these is values between 0 and 255, which are then going to be interpreted by the computer and represented as color. There are other color schemes other than RGB, which is the main one that most people are familiar with. I'll talk about one other in this presentation, but there are quite a few and they've all got different properties. The main ones you kind of need to think about are RGB and then grayscale as well. So when you're capturing digital images, there are a couple of things from a hardware perspective that you sort of need to think about, or at least be aware of, because they can change the properties of the image, images that you're going to use for some purpose, right? So the kind of main ones that I can think of are shutter speed, aperture, capture speed, which is slightly different to shutter speed, image size, as well as image type. Size is the literal resolution of your image. So 640 by 480, 128 by 768, anything like that, right? That's going to change how quickly your analysis is going to go through the images. The bigger an image, the slower it's going to be. And then image type is kind of dependent on the hardware as well. So most often you have snapshot versus rolling shutter images. These are not things you need to worry about so much, because most cameras these days are, well, for most purposes, there's not really a difference between the two. It doesn't really matter, but in certain situations, these are kind of things you need to think about. Shutter speed and aperture, I'm going to talk about in a second. Capture speed is basically depending on the hardware. So once you capture the image, you need to actually extract that information digitally from the sensor and into your computer. And some computers can do this faster than others, depending on, so for you guys, you'll have a Raspberry Pi. So you've got the Pi and then the camera, and then the connection between the two is this ribbon cable, right? It actually takes a moment of time to get the information from the Pi, from the camera to the Pi. And sometimes this is this delay can pose problems and is something that you actually need to think about, because you're now dealing with physical information that's being transmitted from place to place. Shutter speed and aperture are kind of two core things that you need to understand when we're thinking about any type of camera. This is super basic, just what these terms mean. So shutter speed is basically the rate at which a camera takes an image. So thinking about really old cameras that had a physical closer, it's basically light would come in and it would expose the film in the olden days. We're talking about like old cameras, right? For a certain period of time. And then the shutter would go down. Basically, how quickly this happened is the shutter speed. This is an example of the difference between high shutter speed and low shutter speed. So high shutter speed basically means images are going to be less blurry, right? So if you're trying to capture motion, you need a high shutter speed because you're going to reduce the amount of blur in your images. So this image on the left has a high shutter speed, while this image on the right has a low shutter speed. And there is like a balance between the two. Aperture is basically how wide the lens is, how much light is let in by the lens, right? So it's the amount of light reaching the sensor, and on old cameras, this was done mechanically, and on cameras and Raspberry Pis these days, it's sort of not done in software, but the process of capturing the image is different. But the concept is still going to affect your result in the same kind of way. In like old cameras, and really what aperture does is it affects the depth of field. For Raspberry Pi and other similar kind of digital cameras, you don't need to worry about it so much. But what you do need to think about is the relationship. I haven't talked about ISO, but that's because I've never had to deal with ISO on a Raspberry Pi, but you do need to think about the relationship between shutter speed and aperture. So the combination of all of these three things gives you something called exposure, which is basically how well your image responds to light and how it responds to light. So if you've ever heard a term where an image is overexposed, this is what happens. Basically, there's too much light coming to the image. You know, the aperture is too wide, the shutter speed was too slow, and so the sensors all got blown out, right? This is what happens when you have bad settings for what you're trying to capture. This image up here is a single frame image. This isn't an amalgamation of multiple images, but this is what's called a long exposure photography, where basically you leave, you open up the aperture and you leave the shutter, you increase this, you make the shutter speed super slow so the shutter stays open for ages and it captures lots and lots of light. So as things move around in the distance, all that light is being captured by the sensor and recorded. When you leave it open for a long period of time, you get these long trails, right? So that's how you get all these cool like shots of vivid and all the boats moving around and like pedestrians. That's long exposure photography where the shutter speed is super slow and the aperture is quiet. And you have to think differently because, for instance, in the daytime, there's lots of light, right? So your aperture could be less, or your shutter speed could be slightly slower and you'll still capture the same amount of light and images are still going to be sharp. But at nighttime, there's much less light. So what can happen is your images, you're not going to get enough information to do any analysis. And so you might need to increase the aperture or slow the image down, slow the shutter speed down to capture more light, right? In order to actually get enough data to do your analysis. But then your images start becoming more blurry. So other things become harder. So you kind of have this interplay between aperture and shutter speed depending on what you're trying to achieve and the environment that your camera is in. In most situations, you don't really need to screw with shutter speed and aperture, particularly not if you're inside and with a controlled environment, but they are things that you do need to be aware of, and these are settings that you can play around with on the Raspberry Pi very easily, and you can just see what happens as a result. So we kind of talked about digital images, kind of talked about why we use image processing. Now, how do we actually do that, right? What are some basic techniques, and how do we actually take an image and process it? So we use a thing called OpenCV. It's probably, I think it's the world's most widely used image processing toolbox. It's open source. All the code is open. It's constantly being updated. I think we're in OpenCV 4.4 now. And it basically allows image manipulation analysis, as well as a number of useful algorithms that have been optimized for speed and things like that. OpenCV is a C++ and C library, mostly C++, which has Python bindings that provide most of the functionality that C++ does, as well as most of the optimization that C++ provides with being a compiled language versus an interpreted language. So you don't have to worry so much about the speed of the two libraries, unless you're actually implementing complex algorithms, which base Python does become a lot slower. OpenCV has amazing documentation. Everything is available. So it's a really, really, really nice toolbox that is used in industry very like all around the world. So I'm going to start this with some example of actually how to use OpenCV, because I find that more helpful than just talking about theory. So this whole thing's going to be in Python. C++ as well is fine, but Python is easy to understand. So very briefly, you can import OpenCV. You do this. There's one line of code. We're dealing with this image here, this baby Yoda image. imread basically reads the image and loads it into RAM. Your end result, your image, the shape gets loaded as a NumPy array, which is what actually is what all of OpenCV in Python deals with NumPy arrays. So if you're ever dealing with something or need to pass it back into OpenCV in Python, you're always dealing with NumPy arrays. So we can see, and we talked about how an image or an RGB image is going to be some width times height times the channel. We can see that it's a 1600 pixel by 3200 by 3 pixel channel. And this 3 is going to be each layer, which is going to be RGB. Right? This flag basically just means read it using the raw data. There's a couple of other flags which can be used for different purposes. So I think -1 is like read for like transparent background. So if you ever get an image which like has no background, it includes that and things like that. Once you have this image in RAM, you can do some stuff with it. We'll talk about what this does in a second, but just for now, this converts this line of code, converts this image to grayscale, right? And then I can display the image and I can write the image. So this saves it as a PNG file. I take my image grayscale and I save it at this location. And then this is some grossness that allows you to display this code, the image in a loop. All the code will at some point be distributed to everyone watching this lecture, either tonight or tomorrow or something like that. So if you run this code, this little while loop is there so that the image will just stay on screen. So in OpenCV, it's super easy to read an image, write an image, display it. In memory, you can do whatever you want to it. So it's super simple, super intuitive, and super easy to visualize the information that you have. Because one of the things with images, when you're programming with images, you can't like debug in the same way that you can normally like add print statements or add breakpoints, because you're dealing with matrices that are hundreds, if not thousands in size. How you can't read that and see if it's right or not. So the best way you can do it is to actually visualize your output. And OpenCV has super nice ways of doing that, either by writing the image or displaying it. So let's talk about some basic techniques in OpenCV. Obviously, there are thousands of different functions and algorithms that all have different uses. I am going to talk about a very small amount in a very kind of specific manner. So remember, everything I talk about here can be used for other things and should be used for other things. And there are other ways of also achieving what I'm talking about. Or at least the end example, there'll be multiple ways of achieving that. But this is kind of just the simplest way, I think, of tackling specific problems. So for that in context, I'm going to structure this in terms of our aims for this lecture is to talk about segmentation, and really basic classification. There are heaps of other things that OpenCV will allow you to do. These are things you cover in other courses. These are things that you cover if you get out in the field and work in this. We're going to talk about segmentation on a single frame. So we're not going to talk about a movie. We're not going to talk about context between frames, which I will mention at the end of this lecture, but it's just going to be how do you analyze a single frame at one point in time and get some information out of that. So segmentation versus classification. What is this? These are two kind of terms that come up a lot in computer vision. And basically, segmentation is the location of an object or objects in the frame. Right? Segmentation is happening right now for everyone in Zoom. When you have your background on in Zoom, it's doing foreground, background segmentation. Right? So I'm in the foreground, and it's segmenting out the background and putting this lovely starry background there. There's the most basic example of image segmentation. It doesn't know what I am. I have no classification, but it knows something is there and it knows it's different from the background. It's the simplest example of segmentation. You can see here that we have segmentation based on objects, where here it's taken light pole, here it's ground, here's different cars and things like that, right? In this example, it might not know what those objects are, but it knows that they are different to the other objects in the scene. This is kind of a bit of an odd example because there is some classification going on here because it can tell that these objects are the same and these red things are all the same. We as humans know that it's cars and people, but this segmentation might not know what they actually are. It just knows that they're the same thing. So there's kind of different layers of segmentation. It's not just like one thing or another. Classification is what type of object it is, right? So once you've segmented the object, you might want to find out what kind it is. So in this situation, this example on the right here is an example of segmentation and classification, right? So it segments out the different objects in the room and labels them. So purple, you can see it's classified this segment as a bed. These are pillows. These are tables or whatever, right? So you can see that there is kind of an overlay between segmentation and classification. But these also answer kind of the key questions that you often want to answer in computer vision, which is what is my object, the object I'm interested in, and where is it? If you have those two bits of information, then you can actually start doing useful things with your scene, trying to understand your environment. I'm mostly going to focus on the segmentation part because classification is a lot harder and also gets a lot more complicated very quickly. But this is the intuition behind why you do one thing and then get to the next thing. So how can we start to segment objects in scenes? I already mentioned background foreground segmentation. So this is a method that we can use, and there are some functions in OpenCV that attempt to do this. I'm going to talk about really basic color thresholding. Mainly because it also allows me to talk about other things, and also I have some examples later on which are super illuminated by color. Why do we want to segment things by color? Well, one, because they can often tell us a lot of things about the subject, right? We, as humans, often identify things by color. You know, pass me the red pen or something like that. So it's a super easy identifier that we can use to classify objects. In this way, color is kind of part segmentation, part classification, because you already have some information about the class of the object. You might not know it's a pen, but you know it's red. So you're kind of already halfway to classification anyway. However, there are lots of problems associated with color thresholding. So one of the main issues with color thresholding is because colors look different under different lighting conditions. So if something is super exposed, which we talked about earlier, a red object might appear actually white. And so now your color thresholding is useless. The properties of texture, which we also talked about earlier, are going to change the way objects react. If something's super craggly, it's going to have lots of shadows and it might not reflect a lot of light, so it's going to be pretty dark. But under light, it's now going to start to absorb certain parts of that light, and it's going to look different under different lighting conditions, right? So you have to be super careful about the thresholds, which we'll talk about in a sec, because color is kind of something that humans are really accustomed to understanding. You know, if you see a red cup, you know it's red, even if it's not actually red, because you've seen it before. There was context around putting the red cup on the table. And so we can kind of see through a lot of the issues that light causes when it's shown on an object. So simplest example of that is basically if I look at these two scenes, these are all the same color. So this color is light green, blue is blue, and things like that. But you actually notice that under different lighting conditions, they look different. The most obvious example is these two greens, right? Which is basically because this green is the dark green, but it's actually lighter than the light green in this situation, right? So color is not necessarily the best thresholding or the best segmentation, the best way to segment things in a scene. If we look at this orange block, it's super overexposed. So it's actually more white than it is yellow, right? This orange block kind of looks more, well, I think this is yellow actually. I think this yellow block is actually more orange than it is yellow. Right? So we can already see that, and this dark green block is kind of blue. So we've already got problems associated with color thresholding, right? That being said, we are going to talk about color thresholding, but it kind of gives you an intuition as to there's problems associated with it and things you need to be aware of when you start dealing with color. So one of the ways we can get around this, and one of the reasons why I want to talk about color, is because one of the other key concepts in computer vision understanding images is the color spectrum, right? So we all know about RGB, which is how humans interpret color. The three primary colors, red, green, and blue, can basically be used to make up every other color, right? So when we construct images, as I said before, we use those layers. Here's kind of an example of, this is sort of how the relationship between the red scale, this one, the blue scale, oh, this is actually labeled incorrectly. Should be red and blue, I think. Anyway, as well as the green spectrum and how these kind of interrelate. So you can see that if you're high on one spectrum or on the other, you're going to get a completely different color, right? However, as we saw in the previous slide, these are affected a lot by light, particularly the saturation and the luminance of those three channels, RGB, change dramatically under different lighting conditions. So instead, we can use another color spectrum, which is called HSV. There are others, but I'm not going to mention them. But HSV is kind of one of the key ones when we're talking about color, because it kind of throws away a lot of, it gets rid of some of the issues associated with doing color thresholding. The main one is that you can suddenly tell the difference between highly saturated and non-saturated colors. HSV stands for hue saturation. Hue is basically the actual color. So if we look at our chrome wheel here, hue is this kind of top layer. It's usually in degrees and is the actual color. This is kind of a combination of RGB. So all your entire RGB spectrum is basically located around the top of this chrome color wheel, right? Value is almost the grayscale, is the whiteness of it. So if it has a low value, it's going to be super dark. And if it has a high value, it's kind of going to be much lighter, right? Saturation is how much whiteness is in how much, which is essentially how much it's affected by light. So if it has a super low saturation, there's not a lot of light. Super high saturation, there is a huge amount of light. When we're talking about colors, if we go back to the previous slide, these are super high saturation levels. So we now have gone from something that can't describe saturation to something that can describe saturation. And suddenly it becomes a lot more useful when thresholding colors. So why is this useful? On the left is our original Baby Yoda image. And the right is our HSV Baby Yoda image, which is kind of terrifying, to be honest. But it tells us a couple of important things. if we think about HSV spectrum, H is kind of where R was. So everything red is going to be our hue. Oh, sorry, that's actually the other way around. It's the other way around because OpenCV, we think everything in BGR, in RGB, sorry, OpenCV reads in BGR. So you got to go to flipped the other way. I should have mentioned that before, sorry. So red is going to be like your value levels. Green is sort of like your saturation. And so we can actually see where the illumination is in this image, right? So everything red is going to be where it's super highly like illuminated, which is like on top here, things like that. These, this color spectrum under the ears, if you actually look at it, they're pretty different colors. So this is really, really dark. This is kind of dark green, and this is almost orange. Under HSV, these are basically the same color, or at least they're in the same color channel. They're both green. If you looked as we did in RGB, these are totally different. And if you mask them, they're going to be separate in separate channels, and they're going to be considered different parts of the object, right? Or at least different colors. Here, they both have almost the same amount of the green color spectrum because we converted to HSV, right? And the background is all part of that same color spectrum because this is green, and the background is also green because it has the same level of saturation. So hopefully that gives you some intuition about how color can be represented differently between RGB and HSV, and that's affected by light and can be used to your advantage if you know what you're doing in order for color threshold. So how are we actually going to color threshold? What does this actually look like? How is it actually useful? So I have a little video here about, I've taken an image in HSV and I'm going to apply different thresholds. And a threshold is basically saying, let's give it an RGB value or a HSV value that it can't go over. Let's give it a HSV value it can't go under. So we have a range, and everything in between is what you want. Basically, in this video, everything between that threshold is going to be white, which is your mask. Everything above and below those thresholds is going to be black. So this is my HSV image. And here I have a scale. I'm actually changing the max of value. Here I'm changing the saturation, and you can see that what's allowed changes, right? So as I change the min value, I get a different mask. In this situation, I'm trying to find this object, right? I'm trying to mask only this object, so I only want this object to be white. So as I change different values, I eventually settle on a threshold that cuts out everything above what I don't want and everything below what I don't want, right? So I have min HSV and max HSV. So everything above is blacked out, everything below is being blacked out, and I'm left with a single object. This is the basis of thresholding, because I have now successfully segmented this object using its color, right? In this case, the color happens to be red, right? Which you can see from the fact that it's a blue cup, because OpenCV reverses it, right? And now we have a mask. So white is good, black is bad, basically, in this situation, right? So everything, this is an object that our computer can understand. This is the thing we've identified. Picking these HSV values is kind of experimental and changes depending on the light, as we talked about before, but you can kind of find a range where it often works. And HSV provides generally a better response than not, right? What this results in is a binary image. So we've talked about RGB, we've talked about HSV, we've talked about grayscale. Now we're going to talk about binary. Binary is basically zeros and ones. That's it. The only information that you have is zeros and ones, where one is white and zero is black, right? So this image is a lot smaller in terms of how much information is being held, and has a lot less resolution in terms of what kind of information it can represent. But we're going to see in a second, this is actually much more useful than we think. So, oh, I just talked about this. Yeah, so this is just the initial step to segmentation. So once we've found our mask, that mask provides us a segmentation. Right? We've identified where that object is in the scene. From a pixel locator, we don't have a point. There's no XY coordinates. The same, we could take every single white pixel, but that wouldn't tell us very much. There's no connection between all of them. So we still have a couple of steps we need to do, but we've got our mask. Yeah, so as I said, binary image either 0 or 1, and this is used as a lot of input to our OpenCV functions. Most OpenCV functions take your binary image as input. So this is our binary mask for Baby Yoda. All right. Cool. Nice. We've done something. How does this help us? What do we do now? Well, what we can do, and we'll talk about in a second, is we can start looking at trying to use this binary mask to find the edges of the shape. In this situation, if we want to segment out Baby Yoda from the background, this might be a good way to go about doing it. But first, we've got a couple of things we need to look at. The main thing is noise. Now, noise is created because our mask is not perfect. Right? I chose a really hard image because the colors are super muted. There's not like a high range of colors. And so the color threshold on this image is not probably the best way of going about it. You're never really going to get, in most situations, you're never going to get a perfect mask. And that's why color threshold is so hard. We saw on the previous slide that I was able to get a perfect mask of this red cup. In most situations, you can't. You can see here that, if we just wanted Baby Yoda, we've kind of got this extra stuff in the background. We've got this stuff down here, which is the ground. Some of his face has been cut out, has been discluded from the mask and things like that. So, and the other thing with Baby Yoda is he's not one color. So that's kind of a hard thing to deal with as well, because you need to start including multiple colors in the same color scheme, and that's quite difficult. But we're going to do our best. We're going to see if we can try and reduce some of the noise and try and get a better mask for Baby Yoda. So dealing with noise in an image is something that is a huge problem. Comes from hardware issues. You can get noise from hardware because it's the same as dealing with a sensor. A lot of the time what we have to deal with in mechatronics. So we can get noise from image artifacts. So this here is an example of noise that's been generated by a rolling shutter effect. Basically where you try and, we're trying to pull information off the pixels, the sensor pixels, like the literal hardware, too quickly, and they haven't been able to be reset yet. And so you end up with these kind of rolling shutter artifacts like this, which is actually embedded in your image. This isn't sitting something on top that you can just remove. This is actually pixel data has kind of been artifacted and noise has been added. We want to avoid things like this, right? If you have noise in an image, it generally reduces the sharpness of the image, right? It reduces the clarity of the color. You've got little specks in it, little blues, little reds, little greens, whatever around, or in grayscale, lots of little like gray dots lying around. And it reduces the clarity, the sharpness of the edges, which is something we kind of want to avoid because we're going to use edges later on to try and actually identify what an object might be. In a lot of situations, we can model noise using like some probability distribution. Gaussian often works super well. If we're talking about just noise off a sensor. So for nighttime, you often might get a lot of noise. So you might try and reduce that noise and smooth it out using some Gaussian distributed filter, things like that. Here is a kind of an image of what noise looks like from a functional perspective. So if you've got a noisy image, see it's not particularly clear. This is a nice, super clear image. There's not a lot of noise. We've got well-defined edges and high contrast in color. We've got clear whites and clear blacks, which is what we're after. You can see that the result of these are different filtering methods on different images. Don't worry too much about what these are. Basically, you can see that this image has like a high distribution of different types of noise. And this image only has one distribution of certain kind of noise. right? So this noise is distributed evenly, if you want to think about it from like a frequency perspective. So these are like, these would actually be easier to filter out than this, because these noises are like, you can model more exactly the distribution of the noise in these two images, and you can reduce them. Don't worry too much about that, but it's more about images have noise, and we want to try and avoid doing that, right? The noise we get from masks are not noise from the sensor most of the time, right? It's noise from having a bad mask, bad thresholding values, poor choice of methodology, or things like that, right? So we're going to try and reduce the noise and make the edges as clear as possible on our Baby Yoda mask. Before I talk about that, I was going to talk about filtering. So one of the ways we can try and reduce noise on images is by applying what's called linear filters. So basically, you have a kernel, which is a small matrix, usually k by k by 1, so a single, like a matrix in one dimension rather than a block, right? Where we apply that filter, that kernel, to a single pixel on the actual image. The type of kernel determines, the contents of the kernel rather determines the filtering. So if you want to apply different filtering algorithms, the contents of that kernel, the literal numerical values, are going to change, and mathematically we can prove the different effects of those filters, right? This is kind of what's called a convolution, in terms of you start across the entire image and you scan across with your kernel, apply it to every single pixel. Right? So this is one way we can reduce or add noise if we want to. Usually it's a k by k by 1 rather than k by k by 3, excuse me, even for, which you might think might make sense for like an RGB image. You know, let's apply a block filter to our blocked matrix. But actually you don't really want to do this, because a lot of the arithmetic operations are multiplications. And if you have a k by 3 kernel, you start doing these weird things with cross products, where you start summing up each multiple, and then you basically just get undesirable results. So often when you're filtering, you apply a filter to each layer separately rather than to the whole thing as a whole. These are the results of different kind of filters. So this, to go from this image to this image, or this original to this image, you're doing the same method. You're taking a kernel of some size. I think all of these are the same size. I think they're like 5 by 5 by 1, right? And applying this convolution. So you start here, take a pixel. So we might start at this pixel, apply the filter, go to the next one. You do it for every single pixel in the image. The only difference between all 4 of these filters is the numbers inside the kernel. And you can see that they give you totally different results. Now, why do you use one or the other? Well, it depends what you're trying to achieve. Depends on how you're assuming noise is getting captured in your image. And a lot of it is also practice. Also understanding the theory helps, but I'm not going to go into that. So these are different techniques that you can use in OpenCV. I'll talk about the functions in a second, exactly how to implement them. It's very, very simple, but this is the kind of output you're expecting. If you want to filter something, if you want to apply a Gaussian distribution or blur it, if you want to apply a median applied filter, you can do that. So let's go back to, I didn't put an image here. Let's go back to this. So we've talked about noise on an image. Now let's go back to noise on our mask, right? How are we going to actually make this clearer? What are we going to try and do? You can see lots of noise here, good noise up here. There's heaps of noise in these sections, you know, lots of white dots. The edges are not particularly clear. So we're going to try and clear that up. We're going to use what's called morphological operations. Morphological blurring is another kind of image filtering technique. And what they're really good for is clearing up lots of little like holes on binary images. So there are two key kinds of morphological transformations, and then 2 more which kind of build on top of the 2. So we have dilating, by the name, it increases the size of all the white blobs in your binary image. Again, this is why we deal with binary, because you only have 2 choices. Everything, you don't have to think about all the different other values. You can do it in other types, but it's a bit more complicated. Eroding reduces the size of these pixels. It tries and erodes them away. Now, the combination of these two filtering techniques actually gives you some interesting results. So we have opening blurring, which is basically where it's erosion followed by dilation. And what this does is it removes the small white noise. Like when we have lots of little white dots in a large black space, they can be removed by opening. Closing does the opposite. So if we want to fill a space, right, it removes, sorry, the other way around. If we want to remove the little black holes, right, so if we have a large white space and we want to fill it out by removing the little black holes, we can close them out, right? And this happens by choosing a filter and applying this transformation. So let's actually look and see how we do this and how this helps clear up our image. What are we trying to achieve? We're trying to get this noise removal. We're trying to create smooth edges between objects, distinct edges between objects, and this will be used for our blob detection, our actual detection of the object. This is our original image, and we apply an opening filter, right? And you can see the difference in these two spots. So this has gone from super, super noisy, lots and lots of little white dots here, and they've kind of been cleaned up. And this has sort of been made a bit smoother. The dots have been kind of reduced, but actually like increased, but the noise in general has been removed. We apply closing, which, as I said, it kind of gets rid of the small black spots. You can see the difference between the ear here and here. These spots have been removed, right? And if we look here where there's still some white spots as well, they've kind of been removed and made a bit more whole. So if we look in context, the difference between our original mask and our closing image is pretty different. And in general, this is kind of a lot clearer. We can sort of identify the objects as separate, right? And it's going to be easier for our detection algorithms to try and separate out the objects in this scene. So how do we actually find the mask object in our image? I'm going to talk about two core things, which are going to be edges and contouring. Right? And this is the way we actually can go from our mask to actually finding where that object is in the scene. And the end goal is basically like we want a point. You know, we want a single point that can help identify where that object is within that scene, or a couple of points if there are a couple of objects. That's like our end goal here. So edge detection in OpenCV, I'm not going to talk about the theory behind it. I'm just going to talk about what they can be used for and the implementation. So the main two ones for edge detection, and edge detection kind of looks like this. If you look at the top, it basically just gives you the edges, right? It gives you just a whole bunch of white points. Again, it's a binary image. The key thing is that when we do detections like this, there's no like meaning, there's no context between different points. All it is, it finds edges in the scene. It doesn't know which edges are corresponding to which object, doesn't know that there are multiple objects in the scene. All it knows is that there is an edge here. An edge, from an intuition perspective, from an intuition perspective, is basically a changing intensity. So an edge is where something goes from like white to black and then down again. So where there's a sudden change in this intensity, or the gradient, more mathematically speaking, when there's a sharp change in it, that's kind of what the algorithm considers edges. So if that's how you want to think about, you're trying to maximize the amount of sharpness in your scene to kind of give your algorithm a better chance of finding these areas of high contrast and high intensity. There are other edge detection algorithms. There's Ho transforms and Ho circles, or Hoch, I think they're called. This is an example of using the Ho transform or Ho circles to find like these caps. And then you can actually see these dots where they've identified the center of each bottle top. And I'll talk about how we'll achieve this in a second. So we'll go and actually go through an example of how to get to this. So here's an example of me applying canny detection, which is an edge algorithm, to a Wave Yoda mask, right? On the left is with the mask that we applied with opening and closing filtering, and on the right is the original image. can see that by applying a good application of opening and closing filtering can give us a greater like variety of edges that more accurately describe the scene. So here we've actually got kind of the whole outline of Baby Yoda, like almost. There's a bit of kind of random stuff going on here. And while this looks cleaner, there's actually not a lot of information for us to go on. So we were trying to identify where Baby Yoda was in the scene. We'd have a lot more success with this one than the one on the right. So very briefly, contouring, kind of like edge detection, but what contouring tries to do is it tries to give context to a set of points or edges. So instead of points just being points in the scene, we're all the same, it tries to match points to one edge and go, these points, this set of points are part of this object. So it kind of takes segmentation context that we were talking about before and applies it to edge detection. Where it goes, this is an object, and I'm going to try and link all of the points to that object, put them together, right? So it results in a set of separated lines that actually help segment this image. So the result, if we apply contouring to our Baby Yoda, is this. And I've like color coded each contour. And contour is basically just a line, right? So by color. So you can see that the contouring algorithm thinks that everything inside this region is part of a single object. And it's kind of right. If you look at in terms of the way it's segmented by color, everything here is kind of similar-ish color. Here, it's also kind of similar color. We can look at the illumination values here and here, and it's all kind of similar, right? So this is what contouring does, and it sort of tries to actually put a region, put a contour or box around your mask. This example is kind of terrible because it was very hard to find a good mask, right? But this is the intuition behind it. So let's look at an actual good mask and see if we can actually get a central point and a bounding box. Our end result is going to be a blob, and a blob is a centroid. So we take this region and we try and find the center of it, right? Center of it might be, I don't know, maybe here. The center of this region might be around here or something. And if you have a good mask, the center of your region is going to be the center of your object, right? We kind of take a weighted average of all the points in the image, the points XY pixel, and we can find what's called the moment. So if we have a region and we have a central point, this is basically like if you have a circle, you have the circumference and you have the radius. Once you have those two bits of information, you can suddenly do a whole lot of interesting things. You can do polynomial approximation, you can find the circumference, like the length, you can find the radius, and you can also find the center of the object. So let's take everything we've just talked about it and actually apply it, do it properly this time. So I showed an example of segmenting out this red cut. Let's actually see how we do it, and let's actually see if we can arrive at a central point on this object. So this is the code. So I read the image, I convert it to HSV. So we've talked about why you might want to convert it to HSV. You can see I go BGR because OpenCV just is BGR, it's just a thing. And I convert it to HSV. I do a little bit of blurring, and then I apply these lower masks and these upper masks. These values I found using that color picker video that I showed you before, where I was scrolling up and down to try and actually find the best set of numbers that would segment out my image, right? The reason I choose an upper bound and a lower bound is because there's more than one kind of red, right? So under different kind of lighting conditions, red looks a bit different. So these were sort of done experimentally until I found the best range that gave me the most accurate mask under the most lighting conditions. This is where I sum the masks. So high red masks, low red masks. Well, sorry, not sum, but it's a bitwise OR operation to basically take where they both fit together and give me the best region. And I end up with something like this, right? So we've gone from this to this. Now, step 2, we've done the mask. Let's see if we can find the edges. Now, this is much cleaner. This is much, much cleaner. This is actually what you're trying to aim for. You're trying to aim for something like this if you're doing object detection. So this is how you apply a closing filter. All right? If we talk about opening, we talk about closing. I'm going to close off all the objects. You can see here that there's a little bit of black here, a little bit of black here. I want to remove these and make this as white as possible to give the edge detection the best chance to detect the perfect edge. I use quite a large filter, right? Because I kind of want, the holes are quite big, but there's not a lot of them, right? So these are like relatively big in the like ratio to the rest of the object, but there's only a couple, like 6 or 7. So I know that I can use a large filtering kernel to do this job for me. I do another blur to try and kind of smooth out the edges. And then I detect the edges using our canny algorithm. These are some parameters that you kind of tune, and they're sort of things that you sort of need to play around with, but after a while you get a lot of intuition for actually what they might do. And there is theory behind it as well, which again, I'm not going to go into. So this is the result of our edge detection with a good mask. Step 3, how do we find the contours and find the center? So this is actually the result of our image. This is the result of this. We took our edges from the previous slide. We find the contours, which is basically going to be a list of edges where each edge is a list of points, right? In this case, while each of these are individual points, there's only one contour. This is a joined line. So contouring, there'll be a single contour with n points. If there were multiple kind of objects, there might be 2 contours with n plus whatever points, right? So in this situation, we actually just have a contour is of length 1, and actually just has a single list of points, which represent the outline of this object. So now we can start doing interesting things. Now we've found a contour, we've gone from edges to contours, which gives us more information. We can start doing interesting things. So in this situation, I wanted to basically get rid of everything that was too small. You can get a little noise in the scene, little red objects that might pop up. I wanted something that only gets detected if it's above a certain area. And this is kind of, you can test it experimentally, you can try other methods, but this is a nice, really simple method to get rid of little objects in the scene. So if the area is greater than some minimum area that you can find, in this case it's 100, you want to include it inside your analysis. And what I do here is I take the moment of that contour, which basically allows me to calculate the center of that object plus the radius plus other things, other features are associated with this. But in this situation, I just want the center. And these 2 lines of code basically do that for me, where Cx and Cy is going to be the center of this contour. Takes the weighted average of all of these points and puts it in the center. Right? I can define a bounding box also using a contour. If I just had the edge, it would be kind of difficult, you know. I have the center, sure, but how far up do I have to go? How far left do I have to go to define the width and the height of my bounding box? Once you use contours, it can do it for you. And I simply can like draw it on to my image. I draw the bounding box, the rectangle, and the circle onto my image as well. And this is the end result. So that's kind of the accumulation of going original image, mask, edge detection, contours, and centroids. And that's how we can detect an object in the scene. The most simple kind of, most simple example, color detection plus a bunch of other things. But hopefully that's kind of a bit clear, as well as how we can use OpenCV to actually achieve this. Now, there are a couple of problems with this approach. That more questions I want to pose to you guys. You know, so once we have this information, who cares? This doesn't actually mean anything. We now want to do something with this information, right? What do we want to do with it? That's the question. we might have different colored cups. How do we deal with that? Right? If we want to detect cups in the scene, this is only for red. We only have a threshold for red. Do we tune other parameters for a green cup? How do we deal with a clear cup? Right? If there are multiple cups in the scene, how do we deal with those? And another question, perhaps a more difficult one, is how do we start tracking these objects through the scene? If your camera is moving, we're only analyzing the frame scene by scene. Right? So if we actually want to go, this object is the same as in the previous one, we've got two separate frames. We want to track between the two of them. How do we actually start doing this? So there's some questions I'm kind of throwing out to you guys just to have a think about, because while we've done some really basic OpenCV, there's a whole lot of problems on top of that to actually use this information. So I don't know how much longer I've got left, but probably like a bit of time. I'm just going to very, very briefly talk about some more advanced techniques that might be useful. I'm not going to go into how to use them because that would take another very, very long time. But I'm just kind of going to throw out other things that OpenCV can be used for and things that image processing can be used for. So we've talked a lot about segmentation with a little bit of classification in terms of color. But most often we do want classification. We want to know what that object is. And so ways we can start moving towards classification is things with feature extraction. So we can do what's called feature matching by taking an image, our like base image, our ground truth, and start matching sections to another image. So this is our ground truth image. This is our current image. We can see, is this object in the scene? We can use feature matching algorithms to extract useful features from that image, right? And try and match against the scene. So we can start getting classification by going, is this specific object in our scene? The next slide I'll talk about, or I'll mention the use of Haar cascade classifiers. And there are all of these algorithms that OpenCV provides implementations for feature matching, feature extraction, which kind of get us a little bit towards the classification side and away from the segmentation side. Other kind of useful algorithms for segmentation is watershed algorithm, which tries to basically do everything we did in the example, the red cup example, you can do in like 2 lines of code with a proper implementation of the watershed algorithm. And you can also start doing things like what I kind of mentioned about tracking of objects. So OpenCV provides implementation of what's called optical flow, which is how a single pixel changes throughout time. So if we look here, this is actually a vector produced across 5 frames. So this is the same pixel in 5 different frames and produces a directional vector with X, Y, for T. We actually see how things move across time. And that can be useful for tracking objects as we can start predicting their velocity, their position in the next couple of frames once we start having a vector for motion. These are some really basic ones. There are heaps of others as well. And OpenCV has like really cool documentation and examples and things like that. So I just want to talk about this one because I provided code, or I will provide code so you guys can actually run this one. So Hackathon is a feature detector that's probably the easiest access to like simple ML that you guys will have because it's just provided. So Haar cascade feature detector is basically, it's an ML approach. It's not a neural net, but it's a statistical trained model based on heuristic features rather than a learned model, which is what AI does. It suffers a little bit because it is based on this heuristic model. So if the parameters or that heuristic isn't very good, it can not work. It's based on edge detection as well as lines and corners, which is kind of how Haar cascade classifier does. So it extracts lines and corners from an image, and then it learns using statistical models the kind of combination of these particular lines and corners that make up a face, right? And so you can do things like apply the Haar cascade model, which OpenCV provides, and it can do things like face detection and eye detection. I'll provide the code and you can just run it on a computer, run it on the Pi, and you can see it works pretty well, but as soon as you start turning your head a little bit, it can't deal with it because, you know, maybe it expects the edges around the eyes or these two objects, and as soon as one disappears, it suddenly doesn't work anymore. So it has some failings, but it's also kind of a cool little example that kind of shows you what OpenCV and really simple statistical models can do for image processing. I just want to go through some quick examples of things I have used OpenCV for, just in life. Poor kid. OpenCV can be used for understanding focus and the sharpness of images. So I worked at a startup where we were looking at taking, we were basically doing autofocus algorithms. So we were trying to capture pictures like this, and they're like a microscope, and we had to move in and out, try and actually do what video cameras do all the time, your phone does all the time now, which is change the focus to capture the best image. But we didn't have an automated aperture. We had a physical camera that had to move in and out. So you can use OpenCV for things like this because we were looking at the sharpness of an image. And in very brief, the way you can do this is by actually looking at the frequency of an image. You take the Laplace of an image, which is basically things like this. So if you take an image, you can extract out the frequency bands where your X and Y are kind of how like the gradient and the frequency of the image changes, right? And if you do that across the entire image, you can get a value for sharpness. And if you want to think about it, it's actually the variation in the sharpness across the image. And so you can start doing really cool things like that and looking at images in not just the RGB frame, but you can start looking at it in the frequency and the spatial domain and things like that. MTRX 3760 for Electron engineers, you'll do this in third year or fourth year if you're a double. It's basically introduction to robotics, and I came up with this kind of cool approach to mapping or for planning. So we had this robot that was going around, and we were trying to explore this maze, and we would generate like a map of the environment like this. You can think of it like a mini map in like a video game where you're trying to explore, you haven't explored it yet, and so you want to go to the edges of the map. So one of the things I used OpenCV for was to analyze this map as an image and actually find the sections of the map identified in green here that we hadn't actually explored yet, but that also weren't walls. All these black things are walls. So I've gone through and basically converted the map to an image, and then I analyze that image based on where I know the black walls are. You can see here, it thinks there's a wall here, right? So it's actually separated these 2 points into one, whereas really there should just be like one explorative point here. And looks at kind of these edges and find if there's a wall there, and then puts a location. So this is kind of like a odd application of OpenCV, but it was really cool to analyze a map in this way and see if we could get some interesting data out of it. So we could use this to then actually plan where we were going to go and where we've been before, and if we'd explored sections of the map. This, of course, raised some other problems with like tracking. As we move through space, these points would change. So as we move, in this case, the robot's here, if we were moving this way, this point would actually move further that way. And so we'd have to track these points through time, kind of like when I was talking about with the cups and stuff, you start moving around. You have to realize that, no, you have actually explored this area before, you have located this. And the final example I was going to give is something I've been working on recently, which is this Open Cloud robot table organizing challenge. We were basically asked to, we were given a simulation and a robot arm and like objects on a table. And we were asked to, the challenge is to pick up the objects and put them down at certain locations. Really difficult challenge. And as part of the IROS 2020, which is the International Robotic Conference on Intelligent Robots and Systems. And there's a kind of cool application of OpenCV, well, just computer vision and processing that we use to actually pick up the objects. So this is not strictly speaking OpenCV. This is OpenCV plus stuff. In this case, that stuff is a neural net. But it is an application of image processing where what we were trying to do is we take an image of the object, of a object, maybe it's a spoon, and we would try and generate a prediction of how to best pick it up. So if we had the robot arm over the image, we'd use that picture to generate a grasp pose, so X, Y coordinates, as well as orientation, how to actually pick up that object. So this is an example of how OpenCV can be used with other things like neural nets, where OpenCV here is going to be used for pre and post image processing, image sizing, bounding boxing, as well as visualization, which is something that people don't always think about. OpenCV has heaps of tools to help visualize these things so that you as a programmer or as an engineer can actually debug this information. Just as a disclaimer, I was not at all responsible for training this. I was just doing other things on the team, but I thought it was really cool. So I thought I'd put in here. So you can see here that we've got like a heat map of the object where we then generate a possible grasp. So these are the steps from the paper that we used, and it generates this bounding box on actually how to then pick it up, as well as you can't really see on these pictures, but you can see here, this is the orientation that the hand was being predicted to go to pick it up, as well as the point above the object that we should go. This is a bit off. You see the prediction is not great. Really, it should be kind of rotated more in order to get the best grasp. But it's an example of how image processing and images can be used for more complicated things. And finally, I just have a video of how that is actually used. So I don't know if you can see, but here is our prediction. There's a little bounding box around the subject, and we use that to drop down on top of the screwdriver in this case and pick it up. Well, in this case, grasp, but that's an example of how we can use OpenCV to do cool things like that. Thank you for listening. I hope it made sense. Are there any questions?